Hello everyone, and welcome to the next talk in the Data Science Track PyCon 2020. My name is Tamara Thunqvist, and I will be coordinating this section. In this talk, you will hear Ravi Singh, who is a data scientist at HBO Europe. Ravi has pre-recorded his talk, and he will be available for the questions after the talk. Please ask your questions in the comment to this video.
Hi everyone. I guess this is the new norm where we meet everybody virtually. So yeah, I wanted to talk about something which was challenging for me when I started with data science, and I must say, like in some way, it's still challenging for me because there is no one size fit all for this problem, and like every time you have this problem, you have to start with looking at your data, looking at your use case, and you have to find out what suits best for you. So basically, what I wanted to talk about today was imbalanced classes or imbalanced data in machine learning. So what do we mean by it? Like when we say what that we have imbalanced data or imbalanced class, what do we actually mean by it? To explain it, let's take an example where we are trying to predict churn for our customer base, right? And in most of the scenario, what happens is that at the time the churn is taking place, you have very less information about the churn customer as compared to rest of the base. So I mean, let's take an example where you have like 1% churn, and because your business is doing good and everything is going fine, and so we can see here that we have like 99% of the data which is active. So we have a lot of information about one class, which is the active class, but we have very less information about the churn customer as compared to that. And the way most of the standard machine learning algorithm is built is that they expect that you have a proper distribution of classes in your data, and they have this misclassification cost, and they have this cost equally assigned to both of them. So your algorithm will try to reduce that cost and like improve its accuracy. So I mean, take this example basically, and even if I say that all of my customer were active, right, I would be wrong what for 1% of the time. So I will end up with like a really great accuracy. And I mean, you don't have to even apply this data to a great algorithm. I mean, I can build something as stupid as this, where it is just a function which takes customer instance and just replies that, okay, this customer would be active. And I would be right, what, like 99% of the time. And but that's a problem, right? Because the whole idea here was to find who are the customer who's going to churn. And this could be a big problem when you're trying in some other scenarios like bank frauds, or if you're trying to predict some disease which is very rare. I mean, you can see what could be the effect of it if you're not able to find those frauds and not able to identify those diseases. That could have like a very big impact. So it's a big problem, and we are trying to like get over it and understand how it is, how we can overcome that. So to understand this more, let's take a look at it from another way, which is like confusion matrix. I guess, I hope like you all are aware of confusion matrix, because I think it's like one of the most powerful tool. It's a very simple tool, and it's still a very powerful tool to understand what your algorithm is doing. So as we already saw that we have a 99% accuracy, and basically if you can see here that it was able to classify all those customer who did not churn correctly, but the one customer who did churn, it was not able to classify because it just said everything would be active. So basically we can see here that we had a what accuracy of 99%. But if we try to see the precision of this algorithm, basically, which is how many were predicted true and were actually true, and total which were predicted to, in this case churn. So if we basically see that, right, we would see that we predicted 0 as true positive and total predicted were also 0. So we have like a precision of 0, and that's a problem, because that's like a really terrible precision for us. So I mean, even looking at your confusion matrix, you can realize that you have imbalanced classes in your data if you haven't looked in your data before. So what now? Are we going to cry about it, or are we going to do something? So hopefully we're going to do something about it, right? So there are ways where we can overcome these challenges, and one of them is sampling. Uh, yeah. So let's try to take a look at different kind of samplings we can do, which could help us in this kind of scenario. So let's start with undersampling techniques. So the whole idea behind undersampling technique is that you want to reduce the instance of your majority class. So here we can see that we have a minority class, which is, yeah, and then you have a majority class, and you can see the difference between them. It's huge. So what you will do is like you're not going to touch your minority class, leave it the way it is, and then you would select sample without replacement from your majority class and create a new sample, and that will be roughly, it doesn't have to be 1 to 1 ratio, right? But it has to be something which you can compare with minority class, and that is basically undersampling, where you reduce the size by just taking some samples out of your majority class and make them comparable. And there are actually different techniques which you can use uh, to achieve this, basically the undersampling part of it. And yeah, let's try to take a look at few of them and see how they work and how can you use them. So one of them is random sampling, and as you can guess from the name, here you randomly undersample from your majority class. So what does that mean is like you randomly select one of the point from your majority class and then just, yeah, remove it, and then you move on to your next randomly selected point from the majority class, and then you remove it, and you keep on doing this again and again till you have like a good balance between your minority and majority class. So yeah, but I mean, it's a very easy method to implement and it's quite fast also. But the problem here is that we are not we are not under the control that which instance of the majority class we are removing, and we might be removing some of the instance from the majority class which holds very important information, which could be actually important for identifying the decision boundary, and that could be problematic in some scenario. So but if you have like lots and lot of data, you can surely use this, but I mean, always be careful when you're using random undersampling, because there is not a lot which you have uh, under control. So then we can look at some of the techniques which are, let's say, a bit more advanced. So one of those technique would be atomic links removal. So what does atomic link does is that it tries, like it picks up point X and checks its nearest neighbor, and if the nearest neighbor of that point is from a different class and not from the same class, what it does is that it removes the instance from the majority class, because we are trying to undersample the majority class. Like there are options where you remove both the points, but that is not what we want to achieve here. Here we want to just reduce the samples from the majority class, so that's what we're going to do here. So let's walk through this example to understand it better, right? So let's take this where yeah, these two sample are selected, but we see both the points are from the majority class, so we're not going to do this. Then we would pick another point, and I'm just gonna, like, I fast forwarded it to make it quicker. So like in this example, we can see, so both of them are from the same class, so we're not going to do anything about it. And in these cases, all these cases, you can see that they are from different classes. One point is from minority class, another is from majority class. And because we are trying to undersample it, just the majority class. We're not going to remove anything from the minority class. But I mean, in its atomically implementation, you can actually remove both the points, but that's not what we want to achieve here. So what we will do is like we will just remove the majority classes from here, and then we are left with a cleaner decision boundary, like it separates them much better than previously. So, I mean, this method is quite good when you want to separate your decision boundary, but as you can see that it doesn't remove a lot of samples from the majority class, because it majorly, most of the time it works on the decision boundary, because that is the point where you have instance from majority and minority class quite close to each other. So, I mean, you have a better decision boundary, but then you still have like a lot of instance of the majority class. So yeah, keep that in mind when you are trying to work with Tomic link, that it helps you with the decision boundary part, but it doesn't remove that many instance of the majority class. So it could be useful some for some use cases and might not be useful for some other. Yeah, so let's take a look at another approach, which is edit nearest neighbor. This technique is actually used a lot for data cleaning, but like one variation of it can be used for imbalance classes. And basically, it works like the k nearest neighbor algorithm, which you might be familiar with. So for this example, we would take k equals to 2, and like what it does is that for each observation, right, it finds observation and then it's find its two nearest and I'm talking about this point in the majority class because that's where we are concentrating. So what it does is that it finds a point in the majority class and then it finds its two nearest neighbor. Let's walk through the example. I think then it will be easier to understand. So here, so if it found a point in the majority class and then it found like two of its nearest neighbor, and then it's check whether this point, like both, if both the nearest neighbor are from the same class or from different class. Here we can see they both are from the same class, so it doesn't have to do anything. Then what it will do is like it will move to the next point on the majority class, and these are selected randomly, right? So then it moves to this point. So suppose this was the point and then these two are its nearest neighbor, but then we see that it is near to one of the points, so it's not misclassified or like it, it's not that both of its neighbor are from different class. So it will leave that point also as it is, and then it will, because you still have like one neighbor which is from the same class, so it will move to the next point. And here, so here we can see that this point from the majority class is actually both of its nearest neighbor are from the minority class, so it's getting misclassified here. So what it will do is like it will try to not try, it will actually remove that majority class, and you will just you are left with just both the minority class. So in that way it tries to downsample or undersample your majority class. And like we have used k equals to 2, but you can there, I mean, you can use k equals to 3 or something depending upon how much data you have. So that's one more approach where we are trying to downsample the majority class. But then at the same time, instead of downsampling the majority class, you can work with the oversampling of the minority class, right? So let's see what we mean by oversampling. So again, we have the original data set with imbalanced classes. So what we will do here is like earlier we left the minority class as it is and then try to downsample the or undersample the majority class. But here we will do the vice versa. So we will keep the majority class as it is. We're not going to touch it, leave it as it is. But with what we would do with the minority class is that we would select the samples, this time with replacement, and try to increase the instances of the minority class to match that two of the majority class. So basically this. So now you have like the distribution of classes quite similar or comparable. So like your machine learning algorithm could learn much better on it. And there are different ways again here to like learn from it, like how to do it. So let's take a look at some of them. So the easy, like I think the simplest and more the straightforward one here is also random oversampling. So what it does is that it selects samples from your minority class. So here, those will be the green points. It selects those points and samples it and with replacement. So it could sample one instance like multiple times. So it's not that, so one instance can be sampled like 10 times, 20 times, depending upon how much you want to increase the size of your minority class. So your data would look something like this. I mean, here I'm trying to show the number of times they have been sampled by the size. So basically, then you have something, so you have some kind of balance between majority and minority class. Yes. So as you can see here, right, that it's very easy to implement and it's quite fast and it's very easy to set it up and get it running. But again, the same problem here is that you are like you're increasing the same instance. You're like repeating and copying the same instance and again and again and again, and that could result in overfitting of your model. And you have to be a bit careful when you're doing this. You have to make sure that your model is not overfitting, and you get like very great result on your training set. But when you're trying to test it or predict on it, you get like bad results. So keep that in mind when you're trying to use random oversampling. But the good point here is that you're not losing any information what you lost like in undersampling, right? Here you're not losing information. You're just copying the same information from the minority class again and again. But here also you have like some more advanced technique which you can use. So let's take a look at one of them. That's mode or synthetic minority oversampling technique. And what it does is like here again we will take the value of k equals to 1. So we, just for the sake of simplicity of explaining it, I mean, typically you take a value of 3 or something, but like, yeah, it depends upon what kind of use case you have. So let's start with k equals to 1. So what it does that it takes a observation from the minority class and find its nearest neighbor and calculates the distance between them. So take example of these two, right? So it found a instance of the minority class, took its closest neighbor, then it calculates the distance between them, and then what it does is that it multiplies that distance with a random number between 0 and 1. So you have the distance, you have a random number between 0 and 1, and then you multiply it, and then you get a new point on, like, you get a new number on a new distance on the same straight line, and that new point will be your new instance of the minority class. So we get like one more instance of minority class, and this it will do for each of the points. So you end up with much more data point than you originally had. And I took an example where k was just 1, but you can actually take k3. So like it will take 3 nearest neighbor of each point, and then yeah, it will keep on going. So here we are not basically we are not actually resampling the same point, so the chances of overfitting is less, but we are creating new instances with new synthetic instances, so which is good. But the one problem with this one is like it could be very resource hungry and time consuming. So if you have very high dimensional data and lots of that, so it could be a problem in that scenario. So yeah, keep in mind when you're using smooth, but I think it's a pretty good technique to use when you're trying to oversample your minority class. Okay, so we looked at yeah, so okay, so we looked at some of the ways we can downsample and upsample. I mean, sampling is one of the way we can handle this whole imbalanced classes, but there are other ways also. So one such way is like const sensitive learning, and we saw earlier, right? Like we saw that usually most of the machine learning algorithm, they have like a similar misclassification cost attached. So, and if your data is imbalanced, that's not gonna get the result for you. So what in cost sensitive learning, what we want to do is like we want to increase the cost of not identifying those minority class. So if you identify something correctly from the majority class, you have like a cost, but you want the cost of not identify like, sorry, I meant to say like if you have like a The cost of not identifying correctly something for majority class should be less as compared to something which is from the minority class. So you want to kind of push your model or motivate your model to predict the minority classes more, and like this is more, and you can understand it's important in terms of like health when it's used in healthcare and stuff where you're trying to identify different diseases. So for you it's more important and to identify those diseases to be true. So if so you want to find out those instances, so you want to increase that cost. And so basically you want to penalize those classification more where the minority for the minority class than say for majority class. And one way to do that is using the cost matrix. I mean, cost matrix is in some sense similar to your confusion matrix, but here we are more interested into calculating the cost of wrong prediction or the right prediction. I mean, not the right prediction, but yeah, basically that, like what is the cost of which. And basically the algorithm works in a way that it tries to reduces that cost like when it's learning. So that's the whole idea behind it. And here the C indicates basically the cost function, and the first value would represent the predicted class and the second value would represent the actual class. And we can see here that you have like true positives and false positive and false negative. And like whenever we are working with imbalanced data, what we want is like we want to increase the cost of false negative more, because we want to find out those positive classes or the instance from the minority classes. And like you can reduce the calls of false positive, so still you would be okay. And what I mean by that is that something like this, and I mean this is just for example's sake. So so every time is taking the example of churn. So every time there is a churn customer and your model says they will be active, it has a cost of 100. But every time there is an active customer and the model says it would churn, it has a cost of 10. And we haven't put any cost obviously for if they are classifying it correct. But like in a real world scenario, this could be tricky, and this would be the most time consuming part of it, where you are trying to define your cost function. Because depending upon different scenarios, you have to talk to your domain expert and see what should be the cost of it. Like in case of a rare disease, the cost of not classifying that disease could be life, right, or something like that. But to and like if you just say like a healthy person and you identify that they might have disease, the cost of that would be like they are paying extra for the test and like for more tests and stuff. You have to always talk to your domain expert, talk to people who know those stuff, and look at your data and try to find out this cost matrix. And there are different algorithms like which works in this way. So even in scikit-learn you can assign class weights, and you have SVM and you have decision trees where you can actually assign class weights. So you'd assign like a higher weight for the minority class if they are misclassified. So this is again a very good approach when you're working with imbalanced classes. So we talked about some of the approaches quite in detail, but given the time constraint, I want to just highlight few more, but like briefly. So one, like XGBoost, it has become so famous. It's used everywhere, like in Kaggle, that's one of the most used one. And they have few parameter, which is like, which could help with dealing with imbalance classes. And this is basically the ratio of the total negative classes on positive classes. And you can, yeah, you can find out, it's basically the, and you can tune that parameter and try to see what works best for you. So, I mean, that's a good way where it has been built in directly into your algorithm, and you can surely try that out. And one more way would be to get a bit creative with your problem. So instead of making it a classification problem, what you can do is reframe it as a anomaly detection problem. So what you would say, like in this scenario, what we would say is that you have data and the majority class actually is the normal distribution or the actual distribution of your data, and the minority class is the outliers or the anomaly. And in that way we try to find out those. So you can reframe your problem and work with the data in that sense. And or this is a technique, like the hybrid techniques. I think that has been useful for me personally, where instead of using just one undersampling or oversampling, you can actually use the combination of both. So like Tomic link would make your decision boundary more, like it will be more separate, but it doesn't reduces a lot of it. So you can use something like mode to increase your minority class, and at the same time you can make the decision boundary cleaner with Tomic link. So you can try like different hybrid techniques and like combination. You have to I mean, there is no free lunch here, so you have to try it out, look at different techniques, find which is the best. But yeah, surely you can combine different techniques and see if that works out best for you. And I think that's one way to go about it. But before we close this talk, I want to stress on few of the points, that whenever you're doing these kind of sampling, like over or under sampling, make sure that you're applying it only to the training data, right? And so whenever you're splitting your data, train test split, it should be done before you apply sampling, because you don't want to introduce data leakage into your model. You want the model to be tested on like the actual representation of the data. So you want your sampling techniques to be applied just on your training data, right? And we looked at accuracy and we saw that it's not a good metric all the time. So what you can do when you're working with imbalanced data is try to look at different performance metric. It could be F1, it could be recall, but area under curve or ROC curve is like, I think it's a very good. Basically what it does is it tells you how capable is your model in distinguishing between the classes. So it's a good way to give you an idea about how your model is performing. So yeah, I mean, try to look at different metrics instead of just accuracy to see how is the model actually performing when it's working with imbalanced data sets. And one more thing, like when you have categorical values in your data set, try use, there is a one more variation of SMOT, which is SMOT NC, to use when, because uh, SMOT works with calculating the distance between the points. And if you have a categorical value, that will not work out, right? Because that value doesn't, it might, it's not possible to calculate equilibrium distance between a categorical value. So there, but there is a variation of SMOT which you can use if you have a lot of categorical value, or you can try to one hot encode it and see, but make sure that it makes sense, like when you are doing that, and like what you are trying to achieve, you do it. So yeah. And one last thing is like look at the imbalance learn package from Python. It's a contributory package on top of scikit-learn, and it has all this methods which we talked about. So it has methods for all of this stuff, and they have good codes for it. So you can go through the code, understand it, and now you know how these different methods work, and they have a pretty good implementation of it. So you can look at this package and you will have a pretty good idea how to use it, and they have good examples and with visuals and everything. So I think that's a good starting point if you want to start with the look at the code part of it. Yeah. So yes, we talked a lot about imbalance class today, but let's take a quick recap. And so we discussed what is imbalance class. We looked like when there is not equal distribution of classes. So we looked at that. We looked at the accuracy paradox. Basically, you might get like great accuracy, but that doesn't mean your model is doing anything. So always try to check up different other metrics and not just go with the accuracy. We looked at different sampling techniques, both from uh, undersampling and oversampling. And yeah, then we looked at something else, which is cost sensitive training. And basically, that's a good way where you're trying to put the cost of misclassification more for the minority class, and that's how you tell your model is that, yeah, you give it some kind of signal that your data for both the classes is not equally distributed. Yeah, and one point is like be creative with it, like try to combine different algorithm, try to rephrase your problem into, yeah, outlier detection, or yeah, so you have to get creative with it, because As I said, there is no one size fit all where I can say, okay, do this and you will get result out of this. It depends upon your use case. It depends upon your data. So you might have to play with different techniques and see which one works best for you. Yeah, and learn and explore. Like, yeah, as much as time you spend with it, trying, reading different papers, trying different techniques, looking at your data, talking to some domain expert, I think that will help you. So, yeah, have patience, look at your data, go over it, and I think this problem is can be solved. So it's not that difficult. And these are some of the good reads, like some of the papers and where you can read in depth about it, like if you want to read more in depth about this topic. And there are lot more techniques, like I just went over some of them, so it's not like exhaustive list of techniques. There are much more techniques out there and you can read those here. And yeah, and hopefully this will help you with whatever you're trying to do with your machine learning project. And yeah, go learn and explore, and hopefully you will get what you're looking forward to. Yeah, and good luck with your future product. Thank you.
Hello, Ravi,
Hi.
and thank you so much for a very interesting talk.
Thank you. Welcome.
Now it's time to answer to the questions that we got
Yeah,
from our audience.
yeah, that's interesting.
Okay, the first question is, these are some really great pointers. Will these methods also apply to multi-class imbalance classifications?
um, I mean, yes, they will apply to imbalanced, like for a multi-class classification, but you might have to change your approach a bit depending upon like the data you have. So sometime if there are multiple classes and you think like you can group them together and make them balanced, and you're not that much interested into individual class, that could be one approach. And class weights is also very interesting in that sense, where like you can attach weights of misclassification to each of these classes and you can work with it. And like smart also has implementation for multi-class now. So yeah, most of them will apply to multi-class classification.
Great, thanks. And the second question is there a metric to judge how well a dataset has been artificially balanced? For example, bad rating if too much random oversampling has been applied.
Hmm, I mean, there is nothing as such directly for when like after sampling, but you can actually get that using the normal matrices like precision or recaller. So if you see that those number are not making sense, then you know there is something wrong which has happened with your sampling. So there is no, as at least I am not aware of if there is a matrix which you can directly apply after doing the sampling. It's more like, yeah, it's more like when you are doing cross validation and stuff, you can look at the result after applying of your model and then see basically that if it's making sense or not in that way. But I'm not aware of anything which you can apply directly after sampling, but it's more after like, yeah, the training of the model, and then you can check it.
Thanks. So the next question is following. How do you approach imbalanced data in real-world problem? Do you have any experience with high-dimensional data with unbalanced class?
Yeah. So I have some experience with high dimensional. I mean, there could be more like a bigger high dimensional data, but I mean the answer to this is not a very savvy answer. Like it comes down to feature engineering. Like if you have a lot of dimension, you try to select the feature you think are interesting and try to chop it off there. And I mean, after you are done with that, uh, actually oversampling helps here. Like I've seen, because for one of my example it was like oversampling and then using weighted classes for my classifier, that actually helped a lot than some of the advanced technique like smooth. Because the problem with smooth with higher dimensional is that it takes a lot of resources, so it's not like very feasible in a production environment. But like sampling together with class weights helped me a lot, at least. So yeah.
Thanks. We have a few more questions. So the next question is, with a balanced dataset, the predicted classes will be balanced as well, right? For example, half predictions fraud and half goods. Here we must adjust the intercept, right?
Yeah, I mean, I'm not sure if I got the question correct, like fully, but like when we say balanced classes, we are not like I want like a 1-to-1 ratio, right? So, for example, one of the data set I was working with had like 96 to 4% ratio, and I didn't even bring it to complete 50/50. So I bring it to 30%, and then it's the idea of applying, yeah, like trying to add more cost to the misclassification in that way. So we are not trying to achieve a 50/50 balance, and like so we don't want both the classes to be equally identified. The idea behind this is to add more signal of the class which we have not that many signal, and then also it will not be a perfect solution like after you get a prediction. So you might have to go to the route of selecting probability, so you can change the threshold of your probability instead of 50. So that is the way. But yeah, I mean, if he means by 50/50, no, that is not at least I'm working with. So you can increase and decrease the threshold and work with it, if that answers the question.
Thanks. The next question is, do you have any tips for handling imbalanced time series data?
I haven't worked a lot with like time series data in that sense. Like I did, but I have used profit and stuff. But unfortunately, I haven't worked a lot with like time series data, which is very imbalanced. And but like, and what are you trying to achieve with this? If you can explain it, then hopefully I can provide some input. But yeah.
Thanks.
I mean, you can contact me on Slack, like explain the problem a bit more, and I can try to help you on that.
Great. Great that you have this opportunity. Okay, one more question. Do you have any suggestions for dealing with imbalance in regression problem?
I mean, in regression, you are trying to find out a value and not trying to identify a class. So, I mean, it's not a problem there. Like the whole thing with imbalance classes, you're trying to identify one of the classes, and the information about that class is less. In regression, you're trying to find out a value depending upon the independent variable. So, I, I, like, yeah, I haven't seen that pop up, at least in my working in that sense.
Okay, great, thanks. Yeah, we have also some comments that it was a very nice talk.
Yeah, and like if you think like if I got some of the questions wrong, feel free to ping me on Slack, explain it, and then yeah, we can have a discussion. So I will be active on Slack. Just ping me there, and we can have the discussion there. And thanks a lot,
Great.
everybody, for listening to the talk and having me.
Okay. Thanks so much, Ravi, for giving this talk. It was very interesting, and thanks the audience for watching and for asking the questions. Thanks so much. Bye-bye.
Bye.